let's do this button. You have the microphone. Grab the microphone. This will be it. Yeah, good. Okay. And go ahead.
Okay, hello. Um, we're gonna do this, yes. We're gonna look at this group, which is special. I think it's this, yes. Yeah. Okay. So first, for it to be unitary, we need to have u -1 equal to the conjugate transpose, and you also need the determinant of u to equal 1. So we can kind of look at what matrices are going to look like that for that first. So we have the condition that u of t of v.
What does u inverse equals to u dagger imply? What does that mean? And what do we need from determinant of u equals 1?
What do you mean? Like imply as in?
So like what does it actually mean? What does that condition give you?
It gives you.
Yes, I'm asking like what is that condition equivalent to? But that what is that condition equivalent to? And that's something else should be a bit more geometrically clear of what it is doing. Maybe. Like I think you're about to write it down. Right?
Yeah, it's like u of t of w is equal to v w.
Yeah. So that's the first condition is completely equivalent to the fact that applying u preserves all of the inner products.
Yeah.
So you have this assumes you have some inner product space first of all, and then you preserve all of those things, and then determinant u of 1 is okay something about not stretching things. Okay, sure.
Okay, cool.
What is u of t?
It's the matrix at a time.
Okay, so why are we looking at this?
So we can derive it and then look what the matrix has to look like to get the Pauli matrices.
What are you doing right now?
First, well, I was going to derive this and then.
What is this? You're pointing at
some
expression.
The inner product, I was going to take the derivative of both sides.
Okay.
And then show that we can span the tangent space.
Yes.
With like these three matrices.
Yes. So what is it that you're doing then? Like the end goal right now, we're trying
the Lie algebra.
Yes. So you should say to the audience or write somewhere. Right now, we're going to figure out what the Lie algebra of SU2 is.
Okay. We're gonna find the Lie algebra of SU2. Okay. So we have this condition, but then we also have the condition that u of 0 is going to equal the identity, because we want to start at the identity when we make our curve or whatever it is. Okay.
Why do we want to start at the identity?
Because that's where the Lie algebra is located.
Yes, we want to take the derivative at the identity, so we'll set for convenience the identity, like the curves go through the identity at time equals 0.
Yeah. Okay. And then, wait, I'll just go over here. Okay. So first thing we could do is take the derivative with respect to t on both sides of this. This is going to be 0. So then we just get that is equal to 0. And then, yeah. So then that means that wait, I skipped a step. Whoops. Yeah, and then we can look at t equals 0. So at the identity, and then this is just going to become w. So and then using the inner product, we can move these across. Sorry.
Well, it's not just using the inner product, you're using the like adjoint.
Yeah. Well, I didn't do that step yet, but I guess yeah, I could do it all in one step. W, and since this is equal to 0 for any v and for all w, that means like this whole thing has to equal 0, because
Let's
yeah.
Stop for a second. People are still waiting maybe. So question, why is it true that if SV comma SV inner product W is 0 for all V and W, then S has to be the 0 operator? Why does that fall? So you have some operator applied to V comma W 0 for any V and W. Why does that imply that the operator is 0? This is like a classic 247 result. My suggestion is to try and prove it by contradiction. What do we know about the inner product and it being either 0 or non-zero? When is the inner product non-zero? Zero when it's orthogonal, but okay. Well, okay, when is it not definitely not zero? Inner product of something with something else is yes,
Yeah.
when you have a vector with itself. And so this is for any V and W, do you agree? So suppose the operator was non-zero. This means that it does what?
Oh, like the operator applies any vector,
not any vector, but at least some vector.
Some non-zero vector.
Yes, it sends to.
So
yes.
Equal to 0. So the operator applies to that vector.
Yes, that's right. So remember, this is for any V and W. So I can choose W to be equal to the thing in the right-hand component. And I get that that's 0, but that's only true when the vector itself is 0.
Yeah.
Okay. This is like very common results. You prove, if you prove something that holds for any V and W, you can pick a W in terms of the V. Good morning.
Okay, so then we get that this has to equal the negative of this.
Yep.
Which basically means it's skew adjoint.
Yes.
Do I have to move the computer if I move to that board?
Yes, a little bit. So rotate it and maybe move it more to the edge of the table. I think, yeah, all of these cables can be safely moved.
Okay. We'll just keep this in mind because we're gonna need it later. But we also know that the determinant of u of t is equal to 1 for all t. So we take the derivative of both sides again with respect to t. Equal to 0, and there's this identity that basically says that this is equal to the determinant of u times the trace of the inverse.
Not the inverse.
Wait, really?
Should be the trace of the oh, sorry, what? It should be just the trace of u dot.
Really? I searched it up. That's what I got.
Let me see. Sorry, you have trace of u inverse u dot.
Yeah.
It should just be the trace of u dot.
Oh, okay. I mean, it works out the same, so it doesn't matter. Okay, and then we can just again look at t equals 0. So then we get that this is 1 times the trace of u dot at 0. Which means since this is equal to
sorry, you might be right. If it's yes, you're right. Sorry.
okay, yeah, is equal to
This is specifically for u of t an invertible matrix.
yeah. Okay, so this is 1 because this is the identity. So yeah, I guess we just put the 0 here.
I mean, it's not just because it's the identity, that's always true for any u.
Oh, and also, yeah, it's unitary, so we don't even need to worry about that. So then we're just left with the trace of, what was I going to do?
You are taking the derivative at 0.
Oh, wait, the traces can be split up. So yeah, so then you're just left with the trace of 0 is equal to 0. So, yes. Okay. So now, if we kind of look at what the matrix would have to look like, we know that since it's skew adjoint, that these two have to be, the two diagonal ones have to be like purely imaginary. And also, this needs to be the negative of this. So it'll be like I alpha, negative I alpha. And then also, these will also be conjugates of each other. No, sorry. Yeah, conjugates of each other.
Maybe instead of u, that's confusing. You want to use a different letter because
Like
u before was a unitary matrix. Use capital X or whatever you want.
Oh yeah, capital X is good. Okay, and then this will look like I lambda. And then with a little bit of extra steps, factor out an I. You can get that X is going to be in span of, wait, yeah. I gotta remember these.
You're forgetting something.
Am I? Is it the identity?
So these are the Pauli matrices.
Yeah.
But the X.
Oh, I'm forgetting an I. Yeah.
You need an I every.
There we go. Okay. So
Let's stop for questions.
does this make sense? Like you factor out an I, and then like, well, you'll have this b negative b, which will give you, because you factor an I, so the I moves to the top because you divided by I, and then you get this, and then with the leftover gammas, you'll get the 1 and the 1, and then the last one, the remaining part, will be this, and I'll give you that. Yeah.
Why is the derivative of the determinant of u is determinant of u 0?
You can.
It's
take
provable.
The derivative and,
I didn't check it.
In this case, the determinant is just a quadratic polynomial of the entries of the matrix. Wait for me. The determinant is 8d minus bt.
Yes.
Take the derivative. That's quadratic polynomial.
take AD minus BC, where AD, BC are all functions of t, and take the derivative at t equals 0.
If t equals 0, you know that a equals 1, b equals 0, c equals 0, d equals 1, because you start with the identity.
Yes. So you will only be left with what? You'll only be left with certain terms. Yes. This was actually on the 1300 midterm, and I think I struggled with this for no reason. I think I got something in the end, but it took me way longer than it should have.
Okay.
It's a little bit there. Okay, so following, that's a good question. What's another question that people can ask here? I think it's kind of a simple. So we say that x is, okay, first of all, not equal, but in the.
Oh yeah, sorry. Should say
X is in the span, okay? But what do we mean by this span? And what was x? We need to do a bit of a recap. Yes, if you want, you can move to a seat where you can see better.
Oh, sorry.
I'm sorry, this is,
Copy offers.
I feel like that's not
Effective.
that's not the best way to do it. I don't know, maybe we can move this a bit more to the side.
Wait, is there another board behind this?
Oh
Yes. I don't know if that's better or worse.
It is better.
So the following question is, so what did we compute? We checked, we have some conditions on what SU2 is, and then we said, let's figure out what is the tangent space of SU2. What does that look like? Okay, very nice. So when we write in the span, okay, what is meant by this? So x can be represented as what? Yes, linear combination, but with what coefficients? Yes, with real coefficients, right? Because we think of this as some real as a real manifold, right? So all the vectors, all the directions you have can only be scaled by real numbers because we're approximating this with Rn and not something else. So yes, and that's precisely what he showed. He showed that any such matrix can be parameterized with three numbers, three real numbers. Okay. Now what's the next question that people want to ask? So he wrote this in like a really particular way. What was the really particular thing that he did? Initially, you had something alpha, beta, gamma, right? But then he didn't just, did something with a cube. That is kind of simple but special. Okay, well, I guess everyone knows physics with subs. Why did he factor out the I from everything? Why is this significant? Any suggestions? So, okay, let's do the following exercise. So suppose you have a matrix X which is skew adjoint. So write down the condition for being skew adjoint. X. Good. Now look at I times X.
Whoa. I mean, I guess
it doesn't matter.
it wouldn't have made a difference yet.
So let's look at I times X and then take the adjoint, like the Hermitian conjugate of.
Oh, yes.
Okay. What is this?
Sorry.
Okay, now you pause and then you let the audience figure it out. Yes, Ix is self-adjoint. There we go. It's just the same thing. Because the X gets a negative, but then the I gets a negative, and so it's the same. So the point is that he wrote X as the span of I times some self-adjoint matrices. Okay, but why do we care about self-adjoint matrices? This is supposed to be about physics. So why do we care about self-adjoint matrices? In quantum mechanical setting. This is free to anyone.
What, even me?
Well, not you. We discussed it. Well, not just Hamiltonian, but the point is that any observable that you have is always a self-adjoint matrix. And so what we will be interested in is looking at, we'll be interested at some point in looking at self-adjoint matrices, because it's going to be the self-adjoint matrices which are going to be observables, and their eigenvalues will tell me what can be measured in an experiment, right? So physicists, they know that the Lie algebra of SU2 is I times the Pauli matrices, but they instead prefer to work with Pauli matrices rather than I times the Pauli matrices. So they're working with something self-adjoint, which has like some direct physical significance, okay? Instead of the other way around. Would people mind if I turned on some lights? Okay. Good. Did that comment make a little bit of sense? Yes. No? Maybe people haven't taken physics, so they don't care, and that's fine. Okay.
I would say that skew adjoint matrices
Hmm?
from some perspective skewed, but there's nothing better about self-adjoint matrices than skewed.
Yes, there's absolutely nothing better. That's true. But for a physicist, this is what you would prefer from a spiritual perspective, so that you don't have to like take imaginary parts of things, take the real parts. But I guess that's the same thing. Okay. Yes. Yeah. Sorry. Keep going.
Okay. Now these matrices do some pretty cool stuff.
So maybe because you're covering it up.
Oh, you can move that side or
No,
what?
no. On this side at the
Yeah.
bottom, you
Just
have
write
the
the
question.
matrix.
Find the Lie algebra of SU2. So you
Okay.
should write down the answer.
Okay.
That the little SU2 is equal to whatever.
It's like a fancy little, I don't even know. Okay, whatever. I low-key already forgot them. Okay, wait. I think this one is non-diagonal, so this is like, nope, that's a 1. Here we are. Okay, yeah, and then these are just sigma 1, sigma 2, sigma 3. Okay, so
I time. You're
Oh.
forgetting the I.
forgot the I.
That's right.
Okay.
Don't forget to.
All right.
And with that pause, you
Pardon?
won't be able to move it anywhere. After you finish writing on it, you will have to cover that.
Yes. But
This
that's-
part's not that important.
Finish. Yeah. Push it all the way. Okay.
Okay. So there's only one diagonal matrix, which is sigma 3. So we can look at the eigenvectors of sigma 3, which is a little easier than the other ones. You can also like change the basis to make a different one diagonal, but you'll never have all 3 of them diagonal. It'll just make the other 2 not diagonal, so it doesn't really matter, basically. So we have 0, 1. Sorry, it actually doesn't matter, but 2, 1, 0, and then so yeah, and then these 2 eigenstates, because this is an observable, because it's, no wait, I said this wrong. No, wait, yes, is this skew adjoint? Yeah, it is.
You're now talking about some observables.
Yeah.
So what did you assume?
That they're self-adjoint.
No, not that they're self-adjoint. that we know.
Yeah.
That all of a sudden now you're looking at some quantum mechanical problem.
Yeah.
You have some two-dimensional Hilbert space. Okay.
Yeah.
Good.
Oh yeah. Do I have to write that?
Sure. No.
No. Okay.
You should just say it next time. What you're doing.
Okay. Okay. My bad. My bad. This is just like a little part in the textbook. It never even comes back after this. I don't know why it's here. Okay. Whatever.
It will.
Okay. So yeah, -1, 1. And then these states are labeled. I think this one is 0. No, this one is 1. What was this? The Dirac notation?
Yes.
Yes.
So right now, yeah, we will use this notation later. Instead of 1 0, we'll write that. Instead of 0 1, we'll write that.
Yeah. And then if you take half of this, because like usually you just factor out a 2 there as well, and so then you get half of sigma 3, which I didn't do, but it doesn't really matter. It's just a scalar. So then yeah. So then this matrix right here is called and then this one.
Yeah, this is the like. Okay, what you're writing down is not very enlightening.
Yeah.
Depending on all you're saying is that in what scenarios can I get a two-state Hilbert space? One scenario where you can have a two-state Hilbert space is when I have some energy levels, and for whatever reason, it is sufficient to only look at the lowest energy level and the first excited state. Okay, that is sometimes useful because you care about some low energy limit, and so you only care about the lowest two energy states, and so you can approximate your system as a two-level system. And this is what they do in optics all the time. All the optics people, they know two-level systems so well. But really, all that is like they understand, Helmy matrices really well. Whatever. Yeah, that's one. Yes.
Do we call the same two vectors?
Two different things. Yes. That's the point. So in the first labeling scheme, that labeling scheme is often used when you have some energy level, and then you only care about the lowest two energy levels. So you call the one with the lower eigenvalue 0 and the one with the higher eigenvalue 1. Okay, great. In other times, you get a two-level system not because of energy levels, but because you have a single electron and it has like a spin up state and a spin down state. And then, oftentimes use you say that, okay, the third Pauli matrix is the SZ operator, so the operator that tells you if I have up or down spin. And so then you label the states as +1/2, -1/2 to distinguish the state that has spin -1/2 in the Z direction versus spin +1/2 in the Z direction. But essentially all it's saying is all this is saying is you can have two-level systems that appear in different contexts. And in different contexts, people use different notation because it means physically different things. As far as we're concerned at the moment, who cares?
Okay.
Same as upwards arrow.
Yes, and so yes, spin 1/2 and spin -1/2. Instead of 1/2, oftentimes people do down arrow and up arrow in the cat. So this is all it's just that when you see +1/2, -1/2, usually the Pauli matrices have something to do with spin. Or in the other case, it's usually has to do something with energy. Sometimes it can do with both. Whatever. Actually, we'll see an example where it has to do with both.
Okay.
Only will define. No. What is?
If one of them is 0, right? Because otherwise it's not a.
What do you mean? What is well defined?
This, because it has to be an eigenstate.
Oh, why? Oh, it doesn't. I mean,
It doesn't?
No.
It says that in the book. I don't know.
I mean, I think the book is talking about something particular, and it doesn't matter what it's talking about.
Doesn't matter. So should I just skip this?
I don't know. I don't know what this is, so skip it.
Okay. Bye.
What's important is commutator.
Yeah. Okay. So.
Well, they're not very important. We should know.
what was I gonna say? Yeah, so there's no pair of this like sigma of the Pauli matrices that are ever gonna commute. So then there's no eigenvectors that'll simultaneously be eigenvectors for more than one. And then
Yes,
there's
actually,
two
yes.
things we have to.
Let's look at these matrices. Is it obvious by looking at these matrices that, you know, that there is no basis in which they're all simultaneously diagonalizable? It's not obvious? No? Yes. I don't know. In one basis, one of them is diagonal, where the eigenvalues are different, and then the other ones aren't. So that's it. One is diagonal with different eigenvalues, and the other ones are not diagonal. So you probably can't diagonalize them. What if you can diagonalize the other two simultaneously? That would be nice. That's true. But you know for sure you can't diagonalize all three simultaneously. And the other two, it's surely true that you can't do that either. And we'll see that in a moment. Can you just erase all of that? Like,
I asked you yesterday.
oh, I don't remember us talking about this.
Okay. It was like the first thing.
Oh, yeah. I wasn't listening to you then.
Wait, should I skip the lowering thing or should I still do it?
Oh yes. Just tell us what the commutators are. Forget
Okay,
about the
okay,
lower.
okay. That's at the bottom.
That will be important later.
Okay, where's that? 1 second. Right. Okay, here we are. So, yes. If you don't put the I, like if you just take straight sigma 1, sigma 2, then you're going to get that the commutator is.
Is it the commutator or the anti-commutator?
Wait, I was going to do both.
Oh, okay.
Okay. It'll be like 2I, sigma 3, and then if you just swap these, you'll get the other one there, or with the negative if you swap the order. But if you add I, it's a little better because you'll just get like the last one. If you do what I over 2, I think it is, right? That makes sense. Yeah. Okay. Yes. And then there's also the and. Oh.
Yes.
Wait. Sorry.
You would get I over 2, right? Because above you had yeah, is what cancel out.
Oh yeah. This should be yeah.
I over 2.
Yeah. There you go. Okay. Sorry. Yes. But there's also the anti-commutator, which is you just add in the middle instead of subtracting.
So write down the definition somewhere. Instead of using square brackets, people often use curly brackets. So I mean, people write whatever they want, but
do I still put the plus here or?
No, forget the plus. So usually for the commutator, people use square brackets, and then for the anti-commutator, people use curly brackets. Okay, but then sometimes when people want to write some very general expression that is, works both for, so like sometimes you need to use a commutator, sometimes you need to use an anti-commutator. People write square brackets, but then they put a plus or a minus to mean whichever one, and then you get confused because, yeah, the notation in physics is endless, and it's, I don't know, all that.
Okay. Wait, does everyone know what this is? Yeah, okay, cool. So basically, if they're the same, this is 0, and if they're different, if they're distinct, then you get that like 2 times the identity, which again would be removed if you.
It's the other way.
If they're the same.
Oh.
Yes.
Oh, sorry. Yeah. Yes. So distinct ones. Wait. Yeah, distinct ones anti-commute. And then what this means though is OJ squared for any J is going to equal the identity. Right? Any questions?
Yeah. Stop. So this is like you take these matrices, you multiply them together, you add them, you get this. So one thing to point out in the second line, right? What is the second line commutator like? What is the second line commutator mean?
Wait, this one?
Yes. No, leave a comment about that commutator. Anyone? Any comment you like? Comment on the said commutator. What are we taking the commutator of? No, it's not Pauli matrices. It's well, it is Pauli matrices, but what? What are we plugging into the commutator over there in the second line? The first line is Pauli matrices, I agree, but in the second line, it's the Lie algebra of SU2, right? So in the first one, that's just some matrix commutator, whatever. Second line is, remember, we got that I times the Pauli matrices span my Lie algebra of SU2, and so the Lie algebra naturally has some commutator, which is your add x, y, the the representation of the Lie algebra representation of the adjoint representation, or whatever fancy words you want to use. But then, okay, there you get that the commutator of the first vector and the second vector gives you the third vector. Okay, and so in that sense, the Lie algebra of SU2 kind of has this very nice property that you take the commutator of two things, you get the other thing up to some sign, depending on in which order you're taking this.
Yeah,
commutator.
this identity also holds with cyclical commutes.
Yeah, like if
Yes.
you go 2, 3, and then 3, 1,
Yes.
and you'll get the last one.
And so in fact, if you have, remember that it's, if you want to specify some simply connected Lie group, it's sufficient for you to just tell me what the Lie algebra is. What the Lie algebra is, you just need to tell me it's some vector space, and you need to tell me what the Lie bracket, so the commutator on that vector space is. And so very often, and especially in physics, what people do is they say, whatever the Lie algebra is, there's certain basis vectors, and then they just tell you what the commutation relations between all the basis vectors are, and then they can figure out what the Lie group is from there, and that's usually enough. And so that's like a useful idea, where instead of telling you what the Lie group is and what the Lie algebra is, you go the other way. You just tell me some basis elements. You tell me a vector space. You tell me what the commutator between all of them is, and then you get construct everything. Okay. So let's do a lightning calculation.
A what?
A lightning calculation. There's a certain individual at U of T who really likes lightning calculations.
What does that mean?
Don't worry about it. So let's look at some element of I times or minus I times the Lie algebra. So times the vector into Lie algebra. So let's look at v1 sigma 1 plus v2 sigma 2 plus v3 sigma 3. Just write that down. Okay, and let's square this. Whatever that means. Let's square this. And can anybody tell me what we wait, do I want something else? No, it's okay. So people know. it's a lighting calculation for the audience. The audience should use previous results. So the fact that the so can you write down again what the anti-commutator means? So like just write out explicitly, write out
Oh,
the
okay, yeah.
commutator. Like, sigma j, sigma.
Oops.
Sorry, the anti-commutator.
Yeah.
No.
Wait, what do you mean?
No, I meant like AB is a commutator. Write that, but with the J and K again.
Okay.
Just for fun. The fun is that there is no fun. Right? So that is equal to 2 delta JK times A. Suggestions of what the answer should be.
V1 plus V2. Sorry, V1 V2 plus V. Sorry, 2 times V1 V2 plus 2
Okay,
V1 V3.
I'll stop you right there.
This
2
is
times
0
V1 V2. That doesn't quite make
because
sense,
this will
right?
cancel out.
Because remember that matrices don't necessarily commute, so we can't just use binomial expansion.
No, I'm not using that.
Okay. Yes.
Yeah.
That was the correct answer. And let's understand why. Okay. So how do I square two things? Right? I take one thing from, I write it as brackets times brackets. And then I pick something here, multiply it by something here. Okay? But what happens? I have that any two different matrices anti-commute, meaning what? Meaning sigma j times sigma k plus sigma k times sigma j is equal to 0 if k is not equal to j. Agree? So meaning that all the cross terms, right, where I do sigma 1 times sigma 2, I'll have another term which is sigma 2 times sigma 1. And that together is going to give me 0 because the matrix is anti-commute. Yes. And so the only thing I'll have left are terms where I have sigma 1 times sigma 1. Agree? But sigma 1 times sigma 1, that's going to give me 2 times the identity, right? So maybe there should be a factor of 2, and there should be an identity matrix written
No,
somewhere.
because like you'll get 2 equals 2, and then once these cancel out.
Oh, yes. Well,
Because like they'll add, right? OJ's.
yes, I'll have 2 of them. Yes, you're right. Yes.
Yeah.
And so maybe add an identity matrix at the end.
Oh.
It's not just numbers.
Yeah, yeah.
Number times the identity. Okay. People somewhat agree with this statement? Yes. Obvious statement. Good.
I guess I should write these here and then erase this, right?
This is yes, sure. Maybe erase the stuff in green because it's we
No.
remember this now.
Yeah.
And write that identity.
Okay. Orange. So yeah. Oh wait, I guess I should just do
Yes,
this as
use maybe the notation.
yeah. So
So there's this another piece of notation that this is very commonly used. Is often people write v dot sigma, where v is some 3 real numbers. When they write v dot sigma, they mean precisely that v1 sigma 1 plus v2 sigma 2 plus v3 sigma. Common, incredibly useful notation.
okay, and then this is also the norm. So if you only look at v with norm 1, then you just get the identity, which is important. Okay, and then I'll erase this.
V will always have real coefficients.
Yeah, it's because it's an element of R3. Okay.
Oh, right. It's yeah.
Just you won't get the information on
That's right.
Here comes the part that I only somewhat understand. Okay.
So what are we gonna do now?
Yes. To find. 1 second. Let me get this opened up. Okay. What we're gonna do now is we're gonna exponentiate the matrix, because then we can get like the curve, which is where like the tangent line is always equal to the, like you follow the vector field or something like that.
Yes.
It makes sense in my head, but I don't know what it really means.
Remember, we had that the Lie algebra is the tangent space of the identity. Then using right translations. If you had a vector at the identity, you could turn that, you can right translate this vector to other points in your Lie group. And so that way, given a vector at the identity, you got a vector field on the whole Lie group. And if you have a vector field on a Lie group or on anywhere, then you can look at the flow along this vector field. Well, if it's a nice enough vector. And so that's precisely what the exponential map was. Yes? Some people remember this? Yes. Okay. And so we checked in the past that if you want to look at the exponential map of the of a matrix Lie group, then you literally exponentiate the matrix by looking at its Taylor series, expanding it that way. So let's do that.
Yes. Okay. So yeah, we got to use that. So first, if this is to 2p, then this is just going to be the identity if v has norm 1. Okay. And then what we're going to do is we need to go right. So we're gonna, whatever v we have, we can write as theta. Sorry. Here. Wait. Okay. 1 second. Right. So okay, we're looking at e to the I theta v dot sigma. Is that right?
What is this?
This is.
So we're taking an element of the Lie
This
algebra.
isn't a Lie algebra, yeah.
We're taking an element of the Lie algebra of SU2, meaning that it's I times some linear combination of Pauli matrices.
That's why the I is over here. Yeah. And
then you can pick things in such a way that v dot sigma v has norm 1, and theta is okay, whatever. It's
like a scalar, yeah.
So right, yeah, we have the condition. V has norm 1. Okay.
Does this make sense? Okay. Okay. And then we're just gonna use this, and then something cool happens. Oh, and if it's +1, so if this was odd instead, then you'd just be left with just this.
Well, we'll see it. We'll see it in a second. Right?
Yeah. So okay. So we take this, and we use the exponentiation thing. So that's gonna give you the sum to infinity. No. Okay. Theta. Over. Yeah, there we go. Okay, yes. And then we can split this up into the odd terms and the even terms, because this will just become like a negative every time it's squared, or to the 4, whatever. It's cyclic. Anyways. So then this is going to be to infinity p equals 0. Yeah, so that's that. and then these will all just become the identity. So we can just put on the
These are
outside
which terms? These are
the even terms,
even terms.
and then this is gonna be 2p factorial minus.
Maybe you want to add in an identity.
Oh yeah, right here. And then I guess I'll put this in brackets. Oh, they wrote it. Okay. And then yeah, so plus I. Oh. I'm missing a theta. Oh. Yes.
The theta should also be so something.
Oh yeah, it should. Yeah.
Just put it on the outside.
Should I just put it in here?
No, erase it and then write it kind of on the outside separately with its own type.
Oh, okay. So
Yes.
yes. Yes. Okay.
Okay, let's stop for a second. Do people understand what happened in the first term? In fact, can people even see what happened in the first term?
Wait, let me. Okay, I'll write it like that first to begin.
I can see it. Can other people see what it says? Okay. Oh, you, okay.
Yeah, I moved it one step back.
Okay, sure. So, we have this wonderful identity. How do we simplify the first term with this wonderful identity? Suggestions? Yes. Yes. Well, you're simplifying it
You
too
went
much.
all the way to the end.
Yes. So you have v dot sigma to the power of 2p. What will that be? If you take v dot sigma and then you multiply it with itself 2p times. Yes, but we chose v to have norm 1. Do you agree? So you are just left with minus 1 to the p. Well, just write out what we're left with. Yes. Yes, people see how we got that. Yes, because I'm just multiplying v dot sigma 2p times, so I can like split everything into pairs, and each pair will just give me norm of v times the identity. But we chose the norm of v to be 1. Okay, good. And for the next thing, I want to do what? I want to do. Yes, I want to use the same trick for the second one. So what should I do? I want even, like, I know even powers like cancel out. So what should I do?
Yeah,
Yeah,
exactly.
that's right. So you can factor out the v dot sigma. You're left with v dot sigma to the power of 2q, which gives you something. Which gives you just the identity matrix, and then you have the identity matrix times v dot sigma. Okay.
And then it's Taylor series of cosine, and then this is the Taylor series of sine. So yes. So we're just left with Oh, sorry,
Just-
cos. Yeah, I just did it backwards. Yeah. So there we go.
So we've now, exponentiated our Lie algebra to get some Lie group. Great. So in principle, sorry, some elements of the Lie group. So in principle, now you might want to check, did we do this calculation correctly? And so something to check is, check if this matrix is indeed unitary, and if this matrix indeed has determinant 1. But, okay, you can check that yourself.
Okay. Bet.
Because, all that's saying, okay, compute the determinant of this matrix, compute u dagger, okay, you'll get there right there.
Yeah, it's not too hard.
Do people understand what we did and how we did? Yes. This is like a calculation that you do in 4th year physics, and it's a really important. You then proceed to use this formula all the time. Though there you like add various factors of h bar which cancel out everywhere. Still the same formula. Okay. What do we have left? Is it just the physics example?
I also have like a cool picture, but yeah.
Oh yeah, sure. Cool picture.
So if you remember, like in U1, I mean it's not that cool, but it's like a circle, right? And then you have the identity here, and then I basically brings you up, and this is the real line. Wait, no, did I do that right?
Yeah, that's right.
That's right. Okay. Well, it's very similar. It's just a sphere. Wait, is it a sphere or like a 4D sphere? I think it's 4.
What is this here? Which sphere?
But if you compress like one dimension, then we get the same thing where this is I, and then each of the Pauli matrices, sorry, I guess you want to go up, doesn't really matter, would take you in one direction. But yeah, if that makes sense.
Yes. Well, yeah. SU2 is not a sphere. Or sorry.
The group SU2 is diffeomorphic to the 3-dimensional sphere. You
Yes.
can embed it into the 4-dimensional Euclidean space. Just to identify the 4-dimensional space with the algebra of quaternions. And the group SU2 is isomorphic to the group of quaternions of unit length. Well, quaternions of unit length in the algebra of quaternions, which is 4-dimensional, form 3-dimensional.
Yes.
I'm not sure. Was this plan?
No. Right now we'll just I think have some physics comments again, and that's it. We have very little. Huh? Yes. So, I don't know. One thing that you can notice is that maybe if you have, right, you have like 3.
Subgroups?
Yeah, you can also look at like 3 subgroups in
Unitary.
SU2 because you can take a single vector and then exponentiate it.
Yeah, to get
and then you get some
a circle thing
which
at
is
the
like
top.
U1. You have a bunch of subgroups, as many subgroups as you like for the same diffeomorphic to U1.
Yeah. Is there anything else to say about this? No, that's about it. Okay. What should I
erase
erase?
this word and then do the physics comment briefly, and then
Okay, bye.
we'll move on to the next thing in our day.
Okay, hopefully I did this next part right, but we'll see. Yes.
The next part is the same as the part before.
Yeah. just
The difference is that there's no difference.
it looks different though. Okay. So yes. So if you remember from before, wait, can I just move this forward? I don't really need
Sorry,
this.
yeah. Well, yeah. As long as you have the formula, yeah.
Yeah, it's over here. Okay. So if you guys remember, take the derivative with respect to time of psi of t. Then you get negative I. Do I have to say the spaces and stuff? Or can we just
What space?
sorry, like the
H bar? Or what?
yeah, h bar also like
Forget the H bar. H bar is one.
okay, bye. And yes.
This is the what equation? Hmm? Well, no, you can't. This is the what equation, famously. Hmm? Okay. Well, this is famously the Schrodinger equation, yes?
Yes.
But now, looking at it this way, you can recognize that the Schrodinger equation is nothing but what? Well, what does it look similar to? You know, the derivative of psi of t is what kind of object? Where is it living in? Yes. Well, no. Well, yes. Sure. But the like prefactor that I get, the derivative is the thing itself times what?
You want the Heisenberg equation?
Yes, maybe I do, and I guess we'll get there in a moment. I don't want to like. Why is this relevant to what we were just talking about? IH is what? Is what kind of matrix? H, the Hamiltonian is always self-adjoint. So IH is skew adjoint.
Yes.
So it looks like IH should be, you know, something in the Lie algebra of SUN, maybe, if our Hilbert space is finite dimensional. Right now, let's assume that our Hilbert space is two-dimensional. We've been talking about SU2. Okay. Good. Yes. Go ahead.
Should I keep going? All right. So yeah, that's basically what we're gonna do. But how do you spell this? I have no idea. Propagator? I don't
I
know.
think with an A.
With an A? Okay. Yes. This. We're gonna define this. It's gonna be U of t from the real space to SU2. Okay. And the way we're gonna define it is it's going to U of t of psi 0. Yeah. T. Yes.
You fill the spaces.
Yes.
Yeah.
Space is C2.
Yes, like that.
And so U of t, okay, so actually right now we don't know that U of t is in SU2. So based on the definition that we gave you, you know, U of t is just some matrix valued function. Okay. Yes, U of t is just some matrix valued function where it takes my initial condition to what the result after propagating by time t should be.
Yeah.
Okay. So for now, we don't really know that it's an SU2 yet. But this is something we'll see in a moment.
Yeah, so if we differentiate both sides.
So now let's just rewrite the equation above, but with this U of t thing.
Right. Then we use this because that makes sense. Yes. Negative I H. And then instead of writing that, I'll just write this. So Um, wait, I have it written down that I just got rid of this, but look, I don't know how to. Yeah,
That's-
I can,
that's
right? Okay. So then we're left with C is equal to negative H IH U of T.
Why? Because this equation has to hold true for any initial condition that I pick, and the initial condition is constant in time, right? It's just the initial condition. So I get that, you know, this matrix U of T has to satisfy this equation.
Right. So if we look at time equals 0, then we get that 0 is equal to 0, which would tell us that, wait, this is the identity
This
because,
is the identity because at t equals 0, you have to be psi of 0.
oh yeah, okay.
Right?
So
it has
then,
to be-
yeah, so then this would just be equal to I. So then you're left with this is equal to negative IH, which would tell you that negative IH, the tangent space, right?
Well, no. You
No?
already knew that negative IH is in the tangent space because you knew H is self-adjoint. So that you already knew. But it's more so the fact that you had some arbitrary thing U of T, okay, with some arbitrary matrix value function, and then you showed that it satisfies this differential equation where its derivative is, always minus IH times the matrix itself.
Yeah.
But that's precisely the equation for the flow of, that's precisely the ODE for the flow along some Lie, like vector field from an element of the Lie algebra.
Is that right?
So it's yes, right invariant vector field. So everything we've done before was with left invariant vector fields, but in physics the convention is to use right invariant vector field. But nothing changes. You just replace LG with RG, and everything's the same. So that does not imply that IH, and also it would be little s used, not capital S used.
Oh, sorry. That's what I meant to write.
It's yes, but anyway.
Is this right?
This is right,
Okay.
because you realize that U of T has to satisfy the differential equation for us flowing along the vector field given by the algebra element IH. Okay, and so then flow in time along this IH. So the solution to that equation has to be this exponential e to the ITH. Is there a minus sign?
There should be a minus sign, yeah.
That's right. Beautiful. Good. But if H is a 2 by 2 matrix, do we know what the answer is? What this is? If it's a 2 by 2 matrix? Yes? No? Maybe look at the previous board, whatever you can see of it. Right? Yes? No? Comments?
Yeah.
Well, H is what kind of matrix? It's a self-adjoint matrix. And any self-adjoint matrix I can write as a linear combination of Pauli matrices up to some shift by a constant identity.
Yeah.
But H is the energy, so surely I can shift my energy by a constant and not worry about it. So then we can just use that result to get this exponentiation where I write H as some linear combination of Pauli matrices. Beautiful. So now, if you have a two-level system where the Hamiltonian is time independent, then we know completely how to solve this system, like how the time evolved this system.
All right.
Yes, sure. And I mean, yeah, you can also add H0 times the identity if you wanted to. But, yeah. So we know how to solve the system. Okay. So we've now, if you have like a two-level system, we've solved it. Okay. And I guess we have 5 minutes left. Do you remember the comment at the end about
The mag. I wrote it, but
Okay.
like the
I
Zeeman
can
effect.
I can just say it at this point. So let me switch colors to a better color. Okay. So one final physics comment is so sometimes your two-level system, your Hilbert space, is precisely you have like a single electron, and this electron can have spin up or spin down. Suppose that's the case. So my vector space is a two-level system where I have spin up states and spin down states. Okay, and we'll choose this to be once again what this was like 0, 1, and then this was 1, 0.
Yeah.
Okay, in our matrices. And so if I have spin, it turns out people came up in experiment after doing some experiments, people realized that if I put this electron that has some spin in a magnetic field, so I have some magnetic field in B, pointing in some direction B, and then I have my electron E in here, then the Hamiltonian for this interaction of the spin of the electron with some fixed magnetic field should be, do you have the constants? Should
GE.
be, so the Hamiltonian for this kind of interaction of the magnetic field with spin should be
GE over 4MC.
over 4MC, whatever that is, B dot sigma.
Yeah.
Right, so the magnetic field is some vector. It has B1, B2, B3, 3 components. So it makes sense to write B dot sigma. So B1 sigma 1 plus B2 sigma 2 plus B3 sigma 3. Agree? Yes. And then there's some prefactor, which is some number, whatever it is. So it turns out, yeah, this is the Hamiltonian, which couples the magnetic field to spin. Okay? Yes? This kind of makes sense? Okay. So now, and this is what, well, there's 2 comments to make. Let's make the first one about exponentiation, right? Now, suppose I start with some arbitrary spin. Yes, suppose I start with some initial state, alpha spin up plus beta spin down, whatever the state is, right? Where alpha squared plus beta squared is 1, whatever it is. And then after some time, if I want to figure out what how the electron evolves over time in some magnetic field, right? What will I do? I will just apply this e to the minus ith to this. Do you agree? To this state.
Hmm.
You agree with this? Yes? No? But okay, if I do e to the minus ith, this will be what? This will be, so for this particular Hamiltonian, this will be, if we use our formula from before, it's going to be cosine of t times GE over 4MC B, where this is the magnitude of B, times the identity, plus sine
Oh, you need an I.
TGE 4MC B, there's maybe an I here, and I want to do B dot sigma divided by the norm of B. Okay, so this was just the formula from before, and I just plugged in all the correct coefficients. Do you agree?
Wait, why do you need to divide by the norm?
Divide by the norm, because remember you had V, you assumed that V has
Oh,
norm
yeah,
1,
yeah,
and
yeah.
so B has norm not 1, so I divide by B to
Okay.
make that part norm 1. Okay? Right, this is of course the norm of B.
Okay.
But what do I see? I see I have some like cosine plus some sine, where the stuff inside is t times some coefficient. So this coefficient is the same for the cosine and the sine. So I mean, this is as expected. If I evolve for long enough, or if I evolve for long enough time, I will kind of go back to the same state. Do you agree? Just because, you know, if I move t by like 2 pi divided by whatever this number is, then I'll go back. I'll get back to the same value of cosine. So and this is related to this thing about SO3 that we'll talk about some point later, hopefully. That your spin, in some sense, it kind of like it rotates and then kind of comes back to itself. In some sense, whatever this means. Right? You can think of this as like, oh, I'm applying some like U1 subgroup to my state, and then as I keep like going around this U1 subgroup, I kind of go back to the same spot. And so this is called spin precession. And I don't know, people like talking about this. Actually, yes. Why do people say this is spin precession? There's a very particular, I should have maybe said this, that you can, maybe this is more than what I hope to say, but you can like compute. So what we didn't say is that if you take the expectation value of sigma 1 is off, like, sorry, what am I trying to say? What am I trying to say? Very, like, yeah. Usually, sigma 1, sigma 2, sigma 3 are associated to the observables for spin bubbles or spin along x, y, and z. Okay? And so if I have some state, I can look at the expectation value of sigma I in my state. Okay? So I'll get 3 numbers. Okay? And then if my state evolves in some way, I can look at how will these 3 expectation values evolve over time. And if you were to take these 3 expectation values, you get some like vector of numbers. And if you were to plot that, you would actually you would see that it's like some 3D vector that is rotating in 3D space along some circle and kind of rotating back to itself periodically. And that's why this is called spin precession. Okay, that's the comment there. Yes. That's why this is called spin precession. And the comments that is actually given in the book, and so this we'll talk about in more detail later. And the comment that's given in the book is the Zeeman effect, which is as follows. So suppose you had your electron that had some spin, and nothing was, you had some electron that had some spin, and okay, it was just doing its own thing and evolving along some Hamiltonian H0. Okay, and suppose initially this Hamiltonian H0 couldn't tell spin apart. Okay, so this Hamiltonian gave you some energy levels, whatever they were, but this Hamiltonian couldn't tell spin apart, so that electrons with the same, with like opposite spins, had the same energy. Okay, so then these energy states E would be degenerate in the sense that the eigensubspace of E under the Hamiltonian would have dimension, let's say 2, right? So you would have, some eigenstate of spin up electrons, and then some eigenstate of spin down electrons, and then both of those would be eigenstates with the same eigenvalue. So suppose this is the initial set. Okay. Yes. The point is that if I were to take H0 and add Bz times sigma 3. So I had some Hamiltonian, then I would add this term, you know, of b times 1 minus 1. Okay. I will see that all of a sudden, you know, if before two electrons, if before the energy levels were degenerate, meaning that, you know, this, well, in the specific sense of like some state made out of spin down electrons had the exact same energy as some state made up of spin up electrons. Now this would not be true because now I'm adding this term which differentiates between spin up electrons. Those have b times 1 energy, and then spin down electrons get some b times minus 1 energy. Okay? And so then this is often called like Zeeman splitting, where if you had some electrons and they're doing whatever, then you see, you know, this kind of spectrum, let's say. But then if you were to add a magnetic field, then you would see that, say, you know, this line would kind of split into two lines where the energy difference would be, you know, proportional to 2b. Okay, with whatever coefficients. Yes, that's right. And so this is called Zeeman splitting. Zeeman splitting is because this guy Zeeman did this experiment where he was looking at some spectra of, I don't know, something. I don't even remember what it is. You can do this experiment in the second year last. It's a horrible experiment. I hated it. It's very hard to do. You can't see anything. But okay, you look in some device and you see these line spectra. Yeah, you see these line spectra. So you literally see like lines through your device. And then you have some other device which can turn on the magnetic field. And you turn on this magnetic field and you can see that all of your lines kind of split into two lines. Well, you can see it if you do the experiment correctly. I couldn't see it. So. But other people told me that they could see it when they did it. You see that when you add a magnetic field, the magnetic field couples the spin and lets you kind of differentiate between the spin up electrons and spin down electrons in some sense. Okay, so sorry. The main point is that spin couples to the magnetic field, usually, via this b dot sigma term that you add in your Hamiltonian. That's really all I'm saying. Spin precessionist? That's right. I fully agree. It's not clear. And so we'll leave this today on a cliffhanger. Okay. That's good.